Hello. Thank you for joining us today for the second webinar in our machine learning series, Image Processing with Deep Neural Nets. We are very pleased to welcome today's presenters, Marcus van Almsick and Giulio Alessandrini, who are both members of our Image Processing Research and Development team. Marcus is going to give us an overview of applying neural network concepts to image processing, and Giulio will present on real-world computer vision applications. My name is Cassidy Hinkle, Project Manager with Wolfram Research. I will be your online host for this machine learning webinar series. I am joined by several of my Wolfram colleagues behind the scenes to respond to your typed questions during the event and help point you to the resources you need. Feel free to submit your questions using the control panel on the right side of your screen. You can resize the windows to customize your webinar experience. We have had good success with Firefox and Chrome browsers, so if you experience any issues with the screen or audio streaming, you might want to try logging in with a different browser. Today's webinar is a great opportunity for you to learn more about deep learning approaches to image processing. The presentation notebooks and a recording of today's session will be sent to you in a few days so you can continue to build on your understanding and work with the examples. Before passing the microphone to Marcus, I'm going to share our first poll question asking you about your interest in today's webinar topics. Are you interested in deep learning frameworks, in the area of image processing, or in both of these areas? If you don't have a strong interest in either area, you can indicate that as well. When the poll question appears on your screen, please select your response and we'll share the answers after everyone has had a chance to respond. All right, thank you for your responses. I see a big majority are interested in both of these areas, which is great, as we will give a great understanding of both of these concepts throughout today's event. So let's go ahead and do one more poll question as a follow-up. For those that already have some experience with neural net frameworks, this poll question is going to ask which frameworks you have used. Please mark all that apply, or it's okay to just skip this poll if it doesn't apply to you. So Marcus, it looks like a majority of the people that have used the frameworks are using TensorFlow.
Well, then I hope it's going to be my job today to convince them that there are other frameworks out there, just as Mathematica and our built-in deep neural network framework that is built on MXNet, by the way, for those who don't know. Good evening. I'd like to welcome you all to the first part of today's webinar titled Image Processing with Deep Neural Nets. And it's my pleasure, with a slight German accent, to give you the overview and some insights. So basically the look into the tool chest of our framework and give you an introduction on how to utilize all the tools that you find in there. So it's a little bit the nitty-gritty part, the tedious part, and then my colleague with his Italian charm will show you the scope of what we can do in Mathematica with these tools. And he is going to have the pleasure to show really, really nice, fancy examples. Okay, so time is limited. No further ado, let me get started. This is a quick, rough outline of the first part. First, I will just say a few general words. It's titled Prelude about image processing and neural networks, which have a very intimate relationship. Then, in order to basically look into the tool chest, I'll build with you an image classifier from step one all the way through step by step to show you what is needed, what these different tools are for, and how to improve your classifier as you go along. And then once we have a classifier, we'll analyze these networks, not necessarily the one that we built, but also other ones, and see what they can do, what they can't do, what their properties are. And then as a first simple but straightforward application example, I'll show you how to build an image retrieval system with such a classifier. All right, so quick general concept. Image processing is done on a daily basis, unfortunately, subconsciously in the back of our brain. About 1/3 of our brain does it on a daily basis without being aware of it. The brain doing it with 86 billion neurons, 5.8 million kilometers of fibers, wiring, that is 200 trillion synapses or connections or parameters that you can learn, and all of that is done on a bioware, you may say, of doing roughly 1 petaflops or even more. And most amazingly, all of that just with energy consumption of 20 watts. We don't have that luxury with our hardware yet. I work here with an external GPU, but things are going in a great direction. And just to show you the difference between what image processing was just 6-7 years ago, prior to 2012, somewhat the start date, the year zero for image processing and neural networks, due to the Hinton paper and his win of the ImageNet challenge. I'll quickly show you what it was beforehand. Beforehand, image processing was to do like image transformation on the spatial domain, doing filtering, like finding corners in an image, doing shape analysis with the morphological operations, like here finding the spots of a cheetah. Then Holy Grail, which still is somewhat the Holy Grail of image processing, is doing the segmentation. There were all kinds of classical approaches how to find certain segments, like here, hard chambers. Then there was registration, showing basically, oops, this can go down here, showing basically if you have two images, how to make them congruent, how to basically compare data measurements in one image with data measurements in the other image. And then there's a lot of recognition tasks that were already going into the area of machine learning, like OCR, optical character recognition, like what we have here under text recognize in Mathematica. This already included some machine learning and neural networks being part of machine learning. But when I now say machine learning, I somewhat set that apart from the classical machine learning prior to the successes, especially the success that we had in the year 2012, when Geoffrey Hinton and his team won the ImageNet challenge. And since then, it's possible to do things like this. You present an image, and with a command like we have here with image identify, the system can load a neural network and then actually tell what's in this image, something that was unthinkable 10 years ago. So it's a quite remarkable development. Or you can do really funky things like, let's say I have here the image of a horse, and then there are networks out there, which I will introduce to you in a minute, like this network that can transform horses into zebras. This is a trained network. It has been trained on lots of zebra and horse images, and so it can basically convert horses into zebras, and this is how it would look like. So this is the image up there, and kaboom, I suddenly have a zebra on the, well, more African grass there is than European grass or green American grass. You see it, not just the horse changes, but the background does change a little too. And then we have even features that you also would encounter in real living neural networks. For example, you can somewhat mimic the concept of dreaming, basically boosting the activity of certain neurons in your neural network, and thus dreaming up certain aspects of what's stored in the neural network. And I won't go through all of the code. By the way, there is some code popping up in this talk. I'm not going through this code step by step. This is more for those who want to download this notebook later on and do some experiments. So what this is doing is basically, it's a network that, okay, I try to scroll, that takes in an image like what you have seen here. And then it tries to maximize the activity of a certain neural layer, and always changing then via backpropagation, which I explain in a minute, the incoming image, and thereby projecting what's stored in that layer on that image. And if I'm lucky, I can scroll all the way down here, and this would be then such an image. You can see that the forest is almost gone and has been populated with all kinds of exotic animals, birds in this case. And these are features like feathers and so forth that are stored as features in a certain layer of your neural network. That's in this case, Inception Network version 1, and that's then being projected back onto this image. And we'll go into this shortly after. Actually, one should not call it deep dream, but rather a deep nightmare, because most of these images as they come up look rather, well, spooky at least. All right, so that's roughly the scope of what I will talk about this morning or afternoon or evening, wherever you are. And I'll pick up pretty much exactly where Sebastian 3 weeks ago left off, introducing the framework and the technicalities of the Wolfram language implementation of a deep neural network framework. He had basically presented the Linette model, the classical model by Jan LeCun from 1998, that's capable of reading handwritten digits. And we do have such a model built into Mathematica. You can call these things up by Net Model. We also have a whole repository that we'll visit in a second. And when you load this network up, you can just look at it. You see here it's just a chain of neural layers going from input to convolutional layer, pooling layer, and so forth. And once that's loaded, you can directly apply it to your data. And in this case, you'll get even all correct 398 for all the digits being read in. Okay, so far so good. I won't repeat this. What I will repeat, though, is I will take this network and try to cope with a different data set. And see what I need to improve in order to get better results than what I will now get initially. All right, the data set in question is the CIFAR data set, CIFAR 10. CIFAR, by the way, stands for the Canadian Institute of Advanced Research, located in Toronto. 10 stands for the fact that these are 60,000 small images that belong to 10 classes, 10 classes of different type, like planes, ships, cats, dogs, and so forth. And you don't have to go hunting for these data sets on the web. All of this is built into Mathematica and to the resource framework that we have, and that you can then utilize to directly load these things into your system. Okay, so this is just a sample of 6 of these images. You see they're rather small, just 32 times 32 pixels. But if you enlarge them, you can somewhat see, okay, this is a fire truck, so it classifies as a truck. And these are all the different categories: airplane, automobile, bird, and so forth. So that's a data set I'd like now to apply the Linette network on. And the first issue that I have is that the network has an encoder and a decoder, which unfortunately always ends up at the bottom of this implementation. Here you have the chain, and then as an option, you specify the encoder that takes an object, whatever it is, a sound file, an image, some data, plain data, or whatever there's going to be, and convert that into an array of neural excitations, you may call it, if you'd like to interpret that way. And the net encoder basically takes here an image of size 32 times 32 and subtracts a kind of a mean image of a mean value of 0.5, essentially making sure that you don't always have excitatory behavior in all of the image, but that dark regions basically have negative values and thereby inhibit the network. So that's our encoder here, and that's a decoder. The decoder is basically a decoder that takes a vector of class probabilities, to which we'll get, and converts them into labels of that particular class. So up here, you can see what's going on. The encoder that I define here as encode takes an image like here, a little plane, and converts that into a large array of 3 times 32 times 32 values, so a total of 24,704 values. And the decoder does the opposite. It takes an array, in this case, just a vector of 10 digits, and converts that into a label. So here the first instant basically is a category of airplane, so I get the label airplane. And so that's already now what I need to do straightforward in order to convert this to a net that can handle CIFAR data. Then the net, okay, this is a network, so this is the encoder decoder. Now let's quickly analyze this network. For example, I can call up net information and ask for how many learnable parameters are there in this network. And it's quite impressive that basically what you do when you learn a network, you do fitting, and that you have to fit here 650,000 parameters roughly. If I don't fit them yet, if I haven't learned them, I have to initialize a network to just provide random values. And if that's so, I can already plug in an image, but I probably get a wrong classification, a classification saying horse or plane. That's essentially random. All right, so we know how to set up a network. Now I have to get to the next slide. Is this the next slide or the? Yeah, that's the next slide. Okay, this is the next slide. And now I'd like to quickly, before I run and train this network, quickly analyze what steps and what layers we use here and why we use them. What Linette is called, the Linette neural network is called a convolutional network because the prominent layers in this network are so-called convolutional layers. In contrast to linear layers or fully connected layers, it's called linear layers in Mathematica. And the difference is as follows. If I have basically a layer, I have here an array of neurons or activities. And the question is now, how do they connect to the next layer? If you have a linear layer, a fully connected layer essentially, then every neuron or every value gets transmitted to the next, to every value of the next layer. So essentially, if you, let's say, have an input or 9 values coming in and 7 values going out, you essentially have here 7 times 9 values, weights to learn, plus biases for all the neurons up here, so another 7, so a total of 70 parameters that such a fully connected network would imply. If, for example, now the very first layer, the convolutional network layer in my example up there, would have been a fully connected layer, basically taking 32 times 32 pixel values with 3 colors into the first 28 times 28 layers with 20 features, then I would have to learn 48 million parameters. Clearly, a number of parameters that is hardly doable. So the idea is to basically cut away weights, and that's done by, first of all, not connecting every neuron to every neuron, but only connecting neurons in a certain neighborhood given by a radius to connect to the following neurons. So you have a pattern like this, which greatly reduces the number of links. But furthermore, you assume that all the links, this link, this, and this link, have the same weights as the next triple of links in this case. So any links that you can obtain by shifting left or right are basically shared. They are the same, which is denoted here. So essentially, you're learning just 3 connections for the entire layer here. So 3 weights plus 1 bias, which is, of course, clearly much less than 70. That therefore, you can also imagine that the idea is that, of course, now I have far fewer connections, and you can see that instead of having 40-some million, I just have 1,500 connections in the first layer. So that's the benefit of convolutional networks. You just have much less to learn. When do you use convolutional networks? Well, if you have a multidimensional data set that has strong local neighborhood correlations, so if the information is stored in the local relation of pixel values or values in general, then if the machine learning task needs a translational invariance, basically, if you want to have the network treat the left corner of your image the same way as the right corner or the middle part. And last but not least, in order to reduce the number of weights and biases in your system. Last but not least, I'd quickly like to point out that this reduction in parameters only holds for the spatial convolution. It does not hold for the combinations of channels, of input channels and output channels. For example, here I have 20 output channels, 3 input channels that basically every channel coming in is connected via convolution to every channel going out. So in this respect, it's still fully connected, but with respect to the spatial grid, you have a convolution. Okay, let me try to move on. All right. Then we have here element-wise layer, a ramp, which is important in order to introduce a nonlinear aspect in the network, because otherwise it would be just a stack of linear transformations resulting in an overall linear transformation, which would essentially be just one layer. So a ReLU basically puts in a nonlinear aspect, and it looks like this. Basically, it passes positive values just as they are and blocks the negative values. And this is a nonlinearity. And basically, this completes the idea of a neuron, because a neuron, you assume that you collect excitations from your neighborhood. So that's essentially what a linear layer or convolution layer does. And then if it goes above a certain threshold, it will fire depending on how many excitations it receives. And that's this nonlinearity here. And then that excitation is relayed via the axon to the axon terminals. So only in combination of convolutional or linear layers in combination with nonlinear layers do you actually model a neural network. Well, ReLU works beautiful if the values come in around 0. If not, you have an issue. I'll get back to that in a second. And as I said, if you don't have them, you just have a linear layer. So insert nonlinear layers in between linear layers. That's the essence here. ReLU is the simplest nonlinear layer that we have in our system, but we of course have other ones like the logistic sigmoid, the hyperbolic tangent, and many more. Okay. All right, then comes the pooling layer. The pooling layer is pretty much like a max filter in image processing. It just takes in a certain region the maximum response and then essentially downsamples the grid of neurons. So this is mostly used to reduce the number of pixels that you have if you have to cover a certain spatial area. And here, basically, this is a pooling of two patches of 2 times 2 with a stride of 2. So you always move that patch by 2 neurons to the side, thereby downsampling the whole image every time you go through a pooling layer by a factor of 2 in every dimension, so a total of 4. So the benefit is clear. You reduce the number of neurons needed. The drawback is, okay, being downsampled. When you do this, you also destroy spatial information because your resolution goes down, that information is lost. On the other hand, you gain some invariance with respect to translational movements. So movements by, let's say, a pixel forth and back don't matter anymore. The pooling layer would take care of that. And last but not least, any pooling layer is a non-trainable layer. That means it doesn't have any parameters that need training. It's just there and it just works. All right, then last but not least, we have here some simple layers. The flatten layer I don't even mention, or maybe the slide has been just skipped. That basically just flattens the spatial topology of the grid. So I just have, instead of a multidimensional array, just a vector at the end. Here at the end I have just a 500 feature vector instead of neurons that still mimic the grid of the image. So that basically takes out the dimensionality, pretty much like the flatten command in Mathematica. And then last but not least, at the end, after having here 2 fully connected layers that essentially work as a classifier, I have a softmax layer that converts any kind of activity of your neurons that can be positive or negative into positive numbers by basically applying the exponential function and then normalizing it over the sum of all the values. Thereby you get from, essentially you map values from the domain of real numbers into the interval 0 and 1, and they then can be being normalized, can be interpreted as a distribution of probabilities. Like if the excitation of a certain neuron is high, you assume that then that class for which that neuron stands has a high probability in the incoming data. So again, sorry, it shouldn't say pooling layer, it should say softmax layer. It doesn't have any trainable parameters, and it does map from R to the interval 0 and 1. And that's then essentially the last layer that you need. And The next thing would be to train. And to train, you have to have a loss layer. So basically criteria that tells you that you do good or not so good. And interestingly, that is not explicitly given in Mathematica. You don't have to adhere to it or pay attention to it, because in most cases, Mathematica can defer the appropriate loss layer. For example, if you have a classification into classes and you end up with a soft max layer, then it's a safe bet to assume that the loss layer is going to be a cross-entropy loss layer, which essentially measures the difference between probabilities. So the probability distribution of a label saying this is this in this class, so that would be the target that can be provided as an index or just a distribution like this, and then of course a distribution generated by the neural network. And if they if they agree with each other, essentially, let's say here have a high probability for the last class and also index 3, then oops, I should start up here. Then this loss layer will give you a small value. If the probabilities differ too much, then you get a high value. And instead of having an index, you can also, for the target, have a distribution down here. That's the same story, essentially. Of course, there are other loss layers, and depending on what you do, you may want to have loss layers like mean absolute loss or mean square loss and other ones. Okay. Next slide. Time. Okay. Oops. The next step would be to do the training. So this is my network, and I'll now do real-time training on 1080 NVIDIA graphics card GPU. I'll train now those 650,000 parameters by calling up nettrain. This is a network that I constructed up there. This is a Sci-Fi training data set. I want to have all information that I can get via training saved under result. The validation set, which I explain in a second, is specified here. The number of training rounds that I want to run through is specified here. And this specifies if I run it on CPU or GPU. And clearly GPU is better because it's faster and won't strain your patient as much. Now, what you see here while it's training, because training does take time, in this case roughly 30-40 seconds, you see the progress of loss and error rate. If you have now the cross-entropy loss layer, you can calculate the loss, but furthermore, since you classify into classes, you can also measure the accuracy error rate, and they don't really always have to combine. There are subtle differences I don't go into now, but what you can see here is that you have a blue line that goes up slightly again and the orange line that goes down. The orange line is essentially the fit of the training data. Basically, how well do I forecast examples from the training data? The validation data doesn't fit so well. You see it goes up again because you have here an effect that's called overfitting. Essentially, what you do is very much the same thing as if you fit a polynomial to your data. If the model, your polynomial, is too flexible, it will start to fit not just the essence of the data, but also noise into it. And as soon as it starts to do that, then it learns things that are probably not very valuable to forecast yet unseen data. And the yet unseen data, that's the validation data. And if that's not being handled as effectively as the training data, you can see that overfitting occurs. And that's clearly the case here. By the way, this has taken a total of 42 seconds. I did digest 18,626 images per second through the network doing backpropagation, and this is the time evolution of the entropy and the error rate. And you can see the network, here's a confusion matrix, isn't doing great. I mean, accuracy of basically getting 2/3 of the cases right is definitely not something you expect from a network. So clearly this model overfits and it's not doing great. So what do we do in order to get it working better? Next slide. I can do what I would do with when I fit data, I just get more data because more data helps against overfitting. Now, quite often you don't have more data, so what you do is you cheat a little bit, but actually this is very helpful cheating. It's called data augmentation. And data augmentation basically does the following. You have to consider what kind of transformations are permissible to your data without changing its core meaning. And if we, for example, take this image of a plane, then I could very well train also the reflected, horizontally reflected image of a plane, because it's very likely that I not just see plane from this angle, but also from this angle. So this is a perfectly valid data point. Furthermore, by doing this, by basically applying transformations that are invariances with respect to the data type that I'm looking at, I also ensure that the neural network that I train exhibits that invariance later on, that it doesn't favor airplanes flying from left to right over those flying from right to left, for example. Well, you can do reflection, sometimes you can do rotations, sometimes you can do translational shifts. Now, just as an example, this kind of transformation you wouldn't want to do if you were training digits, because reflecting or having a mirror image of a digit is definitely different than having the original digits. But translation is okay. And this can be built into the network. Well, first of all, you can generate this in mathematical data yourself, or even in the net encoder, you can have functions that generate data on the fly, or you can even do it in the network by creating a layer, basically an image augmentation layer. That's the whole story here. It basically takes an image, does shift it around if it's bigger than 32 times 32. And to make it bigger, I have here a padding layer. And I can specify other transformations like the reflection probability. And here I just have a probability of having a horizontal reflection, because vertical reflections would not be as permissible, because usually I don't see trucks or cars or planes upside down. All right, so basically on the fly, I have here more data than the 50,000 that I had initially had. And if I were now to train this, which I won't do because it takes time, losing a minute, you will see that the error rate of the accuracy has gone up, the error rate has gone further down. And just for comparison, I did have to train it a little bit longer because I essentially had more data. You could see that it did do better. You see that blue validation line, the error rate or the loss. No, this is error rate, goes down further than the other one, which was somewhat stuck at this level around 30%. All right, so that's the first trick. Next trick. Let's see. Is a dropout layer. Now, dropout is a pretty fancy idea. The idea is, instead of training one network, you could train several ones and then basically have them all vote on an outcome, and then the majority rules. That idea of taking a whole ensemble of machine learning classifiers and then averaging over them is called boosting. And you can do the very same with neural networks. You would just construct different neural networks and then basically have them vote on the result. In order to make the whole thing faster, there is the idea of dropout layers. You essentially take a network and randomly kill certain neurons in a layer, let's say 50% of the ones in the hidden layer, or a certain percentage whatsoever, and thereby randomly you generate all kinds of networks, and those you can train all at once in net train, because the dropout layer works while you're training, and it basically trains the shared weights. It doesn't retrain them, but it uses them all. But essentially, you're training a whole collection, a whole ensemble of neural networks by using dropout layer. And then once you apply that network, you don't do dropout anymore, and then essentially you do average over the whole list of these trained networks, and essentially you get better results. Not only that, because you have fewer parameters when you train, this is a more regularized, more stable, and less prone to overfitting approach. And because of boosting, you even get more accuracy. So that's what we did here. We did even one more other gadget. Instead of having a convolution layer that has a 5x5 kernel, you can also just have a concatenation of convolutions that do 3x3. It amounts to the same thing. This is actually more efficient and will give you better results because it's more flexible even. Well, having both done, you can see that, well, you gain a little bit. You see down here, it is, you can train longer, it stays stable longer, and thereby you get roughly 2% on average you can gain. Then the next thing to consider is batch normalization. We had in our network, and I pointed out that already, we have these nonlinearities like the ReLU. And the ReLU, they can go astray in a way, because if the activity of the layer in front of your ReLU just renders results in the negative branch, then your ReLU will essentially just block all the transmission. If it's if you just have positive values that are being conveyed, then you don't have any nonlinearity. So essentially, you should make sure that the activity of your network should average around the 0 point here, and that's where batch normalization comes in. Because here I just basically took the beginning of the trained network that we just did, took the front part of the network. We can just see what I did here. Hold on. I basically took the first few layers until I was approaching this ramp in 7. And I was just looking like, what is the probability distribution of the values that go through this nonlinearity? And therefore, I extracted the first part of the network. I generated a whole batch of images, ran them through the network here, recorded the activities, and then plotted the activities as a histogram. And you see, well, they are shifted. And so it is beneficial to put what's called a batch normalization layer in front of such a ReLU. And if you do that, let's see, we gain another few percentage points. So that did help. All right, so what else is there? Well, now comes the obvious. If you want to have better results, you just basically take a bigger network. And the first, there are 2 ways to make a network bigger. You can just make it wider, essentially saying, instead of, let's say, dealing with, I don't know what I used initially, 30 or so features, I can create, I think I used 20 features only. Instead of using 20 features, I can work with 60 features. Having more features, I can learn more, have more information, and that in general should work better. Drawback, of course, is you have more parameters to learn, so it gets a little bit more tedious. But basically, just increasing the number of channels can give you quite a boost, going up here now to an error rate of just 14% or getting up to 86, 87. And here you can clearly see this was a previous learning curve, and now we are definitely almost 4 or 5% under that. So that's one way to go. And next we can, let me see how I'm doing in time. A little running late here. Then I can go for more depth, just having not just the 3 layers, but having 4 layer packages. And essentially, the same story. You can now get even under 10% error rate, and so forth. I think you get the idea how you can improve a data set, a neural network step by step to accommodate the breadth of the problem. Now, quite often, and basically that's the first question I get asked when I talk about neural networks is like, yes, it's all great, but there are so many different neural networks out there. How can I make sense of that? Well, first of all, let me go up here. We do have, I'm just switching to a browser. I'm sorry, my front end is slow because I'm broadcasting. Well, essentially what I'm already quickly describe what I'm hope to see in a second here. We have a network repository where we collect all the well-established, well-functioning, and pre-trained, in most cases, networks that have been published in the literature. And instead of having to train a network yourself, you can basically upload this neural net and then take it from there and don't have to train it yourself. So that way you cannot just quickly train neural networks of, let's say, a few. Here we go. Okay, so that's the which basically shows that you have here not just a convolution network, but a whole module of convolutions. And the reasoning behind this is fairly straightforward. I already mentioned that a convolution network basically takes all the input channels and combines them with all the output channels. So you have the number of input channels times the number of output channels. And for each of these, you have to do a convolution. Now, in order to cut that down, that workload, and to make it more efficient, the inception modules basically segment the number of channels into subsegments, and only in those subsegments they do convolutional layers, well, convolutions. And here in one segment, they do 5 times 5 convolutions, 2 in a row. Then here, basically just pooling. You have 3 times 3 convolutions, and here I just have essentially an identity map. And all of these then are basically combined at the output. So I avoid having to combine every channel with every channel, and I even have now the benefit of being able to do shortcuts or to have a different kind of convolutions with different widths. So that's the benefit of inception. That worked fairly well. Well, it worked fairly well in the sense that you had an increase in flexibility without the increase in learnable parameters to that extent. And then another issue is that if you increase the number of layers, then what the problem is that the learning, the gradient method, the backpropagation doesn't work anymore, because usually either the gradient that you need to learn explodes, gets too big or too small, and then after a certain number of layers, your learning basically stops. And in order to avoid that, the net graph, or the module that they have implemented here, is a trick. It's called, well, it's a residual trick. The idea is basically, if I implement a new layer, first of all, I implement an identity map, essentially, well, an identity map with a ReLU, where I don't do anything really to the data. But in order to learn, I have here a network that trains the deviation from the identity. So I can plug this in. This layer would work right away, but then it would start to modify and learn more. And this identity mapping here makes sure that the gradient doesn't decay as fast. So these are some of the considerations in network design. And now, assuming we have a great network working, we can play with it, and we can analyze what's doable, what's not doable. And for example, here I have an image of a book, and the question, well, it basically tells me now, okay, I did find a book in this, so I did look down here. This is a somewhat tricky case. I have here other cases that I can quickly call up. Here, for example, I can visualize where the clues are that the network used in order to predict that this is an Alaskan malamute. This is done very simply. I basically calculate the output, the probability of this specific class by covering up iteratively areas of this network, of this image, and just seeing how the probabilities goes up and down tells me if I have covered up an essential feature or not. And that's in here at the back of the notebook as a network sensitivity map command that you can then use. And it's pretty interesting. You can, for example, here see that this is classified as a Morgan horse by just looking at the shoulder, and the ears seem to be decisive. Or if you look here at the wolf, the gray wolf, the snout is apparently a big deal. And now I have a porcelain version of a wolf, and this goes way bad. It misclassifies, but knowing what it looks at, you can see what goes wrong. Just looked at the stand down there and classified it as a soap dish. So it gives you some insight of what's going on. Then we can also fool these things. You probably have heard that these neural networks don't really grasp the content of the image as humans do, and I will demonstrate this with a trick. Well, I call this how to cockroach a tiger. Essentially, I have here the inception network. I have a cockroach and I have a tiger image, and the network can classify both of them very diligently. So here, cockroach and tiger works perfect. But what I can do is I can build a network where the lowest layer is the tiger. And then I basically do back propagation and learn that bottom layer, which is the image, to actually give me the output cockroach. And you will see that I only need very few alterations to the original image to fool the network, because the features that are picked up by the first layer are very strongly high frequency layers, high frequency clues that the human eye doesn't really pick up. And therefore, at the end of the day, what I have here trained, hold on, so here I train the whole thing. And you see suddenly, kaboom, it thinks it's a cockroach. And now I create a new tiger, and this is my tiger. But this is not the tiger that you have seen before. It's slightly different. You can hardly see it. It's basically invisible to the eye, the human eye. But for the network, it's now a cockroach, because I have changed some high frequency features that are picked up by the first convolutional network that completely misguide the entire process here. And it's even pretty certain that it's a cockroach. It's 99% certain. And what's the difference between the images of the tiger and this cockroach tiger? Well, you see some, well, almost noise-like high frequency stuff. And last but not least, I'd like to point out that this is then, of course, network specific, because if I come up with another neural network like image identify, this would still work, would still identify this as a tiger. All right, I think I'm running out of time. Just bear with me one more example quickly, which is pretty cool. That is how to visualize the internals of a network, because it helps to know what these neurons, especially the hidden neurons, learn as they are trained on a data set. Now, what's really easy to extract is at the bottom level, which is here just extracting the kernels of the first convolution layer. And you can see that it picks up here edges between complementary colors, lines, somewhat like Garbo wavelets. So this is somewhat typical for any kind of vision task. And it's interesting to see that no matter what you train, the first layers always look pretty much the same. Interesting, the other thing is, and that's why there's a difference between human vision and machine vision, this is just basically picking up at the highest resolution of the image, whereas the human brain or human visual system basically tries to process image at all scales, at all resolutions. And that's why it's not tricked so easily. All right, then there's another way, and essentially this is now Deep Dream on a patch of neurons in the network. So instead of just trying to activate or hype up a whole layer in the network, I can also just go ahead and specify just a part of a layer, which I do here, by the way. And I just define this as a loss function. And by saying I'd like to activate just these neurons in this part of the neuron, and running then the dream algorithm, I essentially dream up the features that these neurons would essentially react on, that they have learned. And for example, if I look now at the 8th channel of the, what was it, layer 4D, then I see that I get to see these features. And here, just for comparison, these are other neurons that you see that they pick up completely different patterns. This is a pattern that looks like a fox face. This is a pattern that looks more like, it's a reptile or turtle that looks like a feather, fluffy thing. So one can see how more complex the features get as you go along. And I think I'll leave it as that. This is just a quick example that you can also find in other presentations. It is the idea of basically taking the network, stripping the last classifying layers, and then just use the intermediate vector or feature vector as some feature function on which you can then do nearest neighbor classification, and that helps you then to retrieve images that are very much alike. So we can quickly run this just for the heck of it. I have here, oops, I forgot to activate the network. Well, I'm not going to run it. Basically, I have here a network that I extracted, just a top part. And if I apply this on an image, I get a vector, which I just unfortunately deleted. And then if I have a whole data set like this here, then I can run a nearest or train a nearest function on that feature vector. And thereby I can calculate a nearest doc function that basically takes an image in, calculates a feature vector, finds the nearest feature vector, and then looks up in the data set what image does it belong to. And that helps you to come up with commands like nearest doc. You just put one doc like here. Forgot the breed right now, I'm sorry. And you get the same breed, Chihuahua or here, a doodle. It's all no problem. Okay, so having gone through this most tedious part, now you're in for a joyride with my colleague Giulio. Please take over. Thank you. And by the way, the Q&A session is going to be afterwards.
Hey, Julia, just so you know, you are muted.
Hello, can you hear me? I hope so. So,
Yep, we can hear you.
Great, that's better. Let me go full screen. So thanks to Marcus, he took all the basically hard work on himself. So I can basically start from what he built and what Sebastian built last week, 3 weeks ago, to show you some real world models that have been converted to work in our framework and that you can build yourself or train yourself if you want. So a quick, let me see. A quick outline of what I'm going to talk about today. First, let's move beyond simple classification. We've been seeing standard classification now in every possible way. I want to show a bit more what you can do with the standard feature extraction pipeline on an image and how you can use those features to predict or let's say infer, compute a great number of different features. We are going to look at first feature-to-feature conversion, some landmark regression for facial key points. Then I want to look at pixel level processing. One would be image colorization, and the other one would be pixel level segmentation. And oh, sorry. And the final task I want to look at is object detection. That is kind of a combination of regression for bounding boxes and standard image classification for the classification of the object within the bounding box. So I want to start with the simple model, which is landmark regression. This model is basically a standard feature extraction pipeline with a convolutional network. And on top of this, you have a classifier that is not predicting a class, so it is not predicting probability distribution, but is directly predicting numerical features on the image. So let's have a look at how this can be done in the Wolfram language. So this is the model I'm using. This is the vanilla CNN for facial landmark regression. Is available in Linette Model. And if we look at the first part, the feature extraction part, we can see that this is basically convolutional network very similar to what Marcus showed you before. So we have a bunch of convolutional layers. In this case, we have 4. We have an activation with an absolute hyperbolic tangent, and the max pooling layer to downsample the feature maps. After this part can be labeled feature extractor. After this part has done its job, then we use a very, very small classification network. You can see these red layers here are the fully connected, the linear layers that are predicting the features. And These layers are basically used to convert the feature maps into, you have this flattened layer that flattens the features maps into a big vector, and then we compute the regression features on those on this big vector. Okay, first thing, this model has a specific requirement, and this model requires data to be standardized. And the way we can handle this within the framework is using some extra parameters in the net encoder, but I don't think have been shown so far. So I wanted to quickly check on these. Net encoder supports a mean image that can be a number, like a color, or can be a full-fledged image that will be subtracted from your dataset, and a variance image that can be used to standardize, like bring the dataset to one variance before you send the batch to the network. So we can have a better look at what we're using here. Like the mean image is probably what you expect, and the variance image captures the Hello? Hello? Can you hear me now? Okay, sorry, my headset had a glitch. I was trying to figure it out. So what we have here is, as I was saying, like a standard normalization for the dataset. Once this kicks in, we can send the data to the network. And given that this network predicts absolute coordinates in the 0-1 range, we want to define something that we have also not seen yet. It's a quick post-processing step that will take the output of a network in the 0-1 range and rescale using the image dimension of the image. And I'm going to use many evaluation networks in this talk. I'm not going to explain all of them because they can get quite complicated. Just want to say that it's very easy, given that this framework is built in the language, to use all kind of image processing functions that are already available in the language. So in this case, it's pretty simple. I just create this evaluation function. And then what I do is I run it on the network, and I see that I get 5 scale points. And if I alight them on the image, I see that what I just did is to detect the 2 eyes, the nose, and the boundary of the mouth. So this is kind of not too many features. We have also more complicated networks that can detect up to 20 features in like landmarks on the image. But I just wanted to start small and show what a simple addition to a convolutional architecture can do. And this is fully trainable in the framework. It's also very fast to train. Another example that I want to show after this is slightly more complicated. Or we may say way more complicated, but actually now we are going to look at the inside this architecture, and we can see that there are not so many new concepts compared to what we've seen already. So this is an image colorization network. I think it's called ColorNet. And I picked this because the authors are doing something very interesting here. So they have a standard feature structure pipeline, which is these like purplish layers here. And these layers are extracting low-level features from the image. And then these features are sent to 2 different tasks. They are sent to mid-level features and then to a colorization network that is upsampling and converting those features to colors. But they are also sent to a global classification network. And why this? Because this way we can basically have a built-in prior generator for the image within the network. So these colorization tasks will not be just dependent on the pixel content per se, but we also have the advantage of prior knowledge from the classification network. But for example, we'll say that this is a night scene or an autumn scene or an indoor scene. So like the color palette may be affected by this. Let's have a look at how this can be done. So first thing, we need to know a little bit of color science, and lucky for you and me, this happened to be my expertise. So if we check this colorization problem, if we look at it in a more general term, what we see is that we have a 3D distribution of RGB colors, and we want to go here from just a 1D distribution of luminance levels. But working in this RGB space is quite complicated because we see that this is intrinsically a 3D problem. And we can greatly simplify this problem by using some color science knowledge and convert this image to a luminance chrominance space like LAB. And LAB or lab, it's a space where luminance is decoupled from the color component. So you see that this would be the luminance very close to the grayscale values in the image. And the two color components are basically the distance from the center here. So I just have a line in the center, which is decoupled from the colors, and I want to predict the lateral translation with my network. So how does this start? First, I have to create a standard feature extraction network. This is very, very simple, very shallow. I have 1, 2, 3, 4, 5, 6 convolution layer to extract the features and standard ramp for activation. These features will be shared. These are the low-level features that will be shared by between the mid-level features and then the global features for the global prior. One small difference here that we are not using, but we are using here it is, the stride parameter in the convolution layer that basically makes the kernel jump from 1 pixel from 1 pixel to the next, from 1 pixel to the one after the next, and this effectively increases the spatial range, of the convolution layer, and makes it so that we don't need the max pooling layer anymore in this type of model. The mid-level features are just a standard fixed size convolutional network. One thing to notice is that in this model, we are compressing not in the spatial domain, but in the channel domain. So basically, all the information that comes to these 512 channels is compressed to 256. So this enforces an information compression and distills the information. Then we have the global feature, which is a slightly smaller convolutional network, followed by some standard classification done via linear layer. And when we put all together, we can use all this with the colorization network that takes all the features and upsamples them and use more convolution to go from features to the chrominance values. So, okay, all this to say we have the colorization network, let's try and use it. So we get a nice dog. Actually, let's look at the dog before. I convert it to grayscale, and what I hope is to recover this color information. So I create here another small evaluation function that is adding the luminance back and is putting the channels all together. So what we see here is that we miss some kind of small low-level details, like the eyes were like browner, here like kind of duller. But overall, it got correctly the shade of fur and the background. And we can even check using our image processing functions the distance between the original and the recolored image. And we see indeed that the eyes were not pretty correctly, but most of the background and dog fur is fine. And we have a median error of 1% across the image. Why did I waste a little time illustrating the network structure? Because first, I think it's interesting to see how we can put things together and also real-world models together. And then because it's very easy in the Wolfram language to use them and do surgery operation on them and alter them without having to retrain or without having to do any low-level operation. So I show that we have a global prior plus local features, but there's nothing that forces us to take them from the same image. So here, for example, I'm using some surgery function to split the network in different parts and send the original image in input to the low to mid level colorization part, and the low to global level and global prior part is taken from a different image. So here, for example, I use a different dog. This is a dog on a bluish background. It's behind the sea. And now I want to see if I can use some of the color palette from this image to predict the color of the different image. And you see here that basically the grass now is not picked correctly as grass because I'm forcing the network to use different priors and get this bluish tint. Or like this kind of thing is a sandy. I've seen many images in the training set. They have kind of a sandy beach and then the sea behind. So it's going for something like that. Let's move to another task. We've seen classification. Let's turn it up to 11, and instead of building one classifier for the whole image, we build one classifier for each pixel. This is basically what semantic segmentation is doing. What we are doing here is using the standard convolutional pipeline to create features again, but then we want to use those features on a much bigger feature map that will be converted in many class distributions. In order to do these tasks, I'm using a specific model that highlights interesting features that you should pay attention to when you train these very deep networks. We've seen across in the literature and over the years that deeper models are usually better, but there's a limit to that. Like at first, people started adding layers and then greater and greater accuracy. But after a while, people realized that there was a diminishing return, and this was for a variety of reasons. First, adding more layers add extra memory and training costs, which is not a limit to the model per se, but it's a middle to how fast you can test and train new models. Then you have intrinsic issues with this because features map get increasingly small the deeper your network. And if you don't make them smaller, then again you run into memory and training time costs because the networks become very big. Then there's a diminishing return in accuracy. So you don't get linear improvement by adding more layers. So the last improvements on ImageNet that were done following this let's add more layer approach. So like a few % improvement, doubling the amount of layer, and which is something that you cannot do to infinity. And then you have a problem, which is a problem of vanishing gradients that Marcus briefly touched on before. And actually, the resonant architecture was introduced exactly for this reason. You want to limit this vanishing gradient issue, or also the inception. They follow basically two different approaches. One combines feature by concatenation, while the ResNet combines the features by summation. Still, if we look at this plot that is taken from this paper, wider or deeper, and where the authors actually are wondering like how to improve on the standard ResNet model. And this is the key point. We see that the gradient is still vanishing for very big networks. That means that we are not truly training this network end to end, because certain layers actually freeze during the training as soon as the corresponding gradient is 0. So this tells us that is not an exact science to pick the right architecture, and there's no clear way. It's not that deeper is always the better or wider is always the better. And the model I pick here tries to strike a balance between depth and width. And this is pretty shallow for a deep neural net. This has just 17 residual units, all those ResNets. But this was guaranteed to train end to end. So when we propagate the gradient back, the changes affects all these blocks. And once we extract the features with this type of residual network, then we use we have to compare them to the set of probability distributions. So what we do is we use this transpose layer. You see at the end of the network, you have 21 channels that correspond to the 21 classes that I'm trying to classify, and the feature map is 63 by 63. So what I want here is to convert these 21 channels in the 21 probability value for the classes in the pixel. So in the end result is a probability distribution map that I will threshold to get the segmentation out. So let's see. Let's use this test image of the cat and the dog. This has slightly bigger evaluation function because I have to probably rescale and threshold all this probability distribution. This will be provided in the notebook. I compute the segmentation. This takes a little while. And once it's done, let's run this right away. Okay, here I see that I classify like 3 different regions that are this mysterious 1, 9, and 13. Let's see what they correspond spatially. Okay, they seem pretty much overlapping with the objects in my image. There's slightly doggish pixel here. I don't know why the network got confused, but overall we are quite fine, I would say. And here, let's see if this corresponds to the right classes. Yes, the black is background, red is cat, and this green is dog. So we did a good job. Let's see, how much time do I have here? Oh, yes, I have still a lot of time. So after this, my final model for today will be kind of, let's combine together all the things we've learned to build a kind of a higher task network that has to combine both object, the object detection and the classification. So what are the ingredients that you need to build a proper object detection functions? I mean, you need at least to do 2 things. You need to predict where objects are, like if an image contains objects, where they are, and the exact bounding box of the object, because you want to know where an object begins and ends. But this would be pretty trivial. Usually we also want to know what the object is, so we need to embed also a 3rd class, which is a standard image classification, but this time on the bounding box. The model I picked to illustrate this is the YOLO network. Oh, yeah, here it is. YOLO stands for you only look once, and the idea is that with a quick look at the image, you are able to infer a great load of information. So how this network is structured? This is, again, a quite short convolution network, but makes use of something that I'm just mentioning here, but we could say a great deal about that, which is a skipped connection or shortcut connection. And the idea is that you may want to adjust your models to have features at different scale talk to each other. So you may want to connect like more low-level features at the beginning, like local, to some of coarser features at the end. And this way, you don't have a result that is directly depending only on the coarse features, but you can also directly see the local features. And this is what this model is doing, basically. Once the features have been computed, those are sent to the, yep, here it is, the final module, which is doing the 3 things I mentioned before. So we want to take those feature maps and convert them to coordinates for the bounding boxes, the probability for the object to be in the bounding box or not, and the condition probability of the objects pertaining to a given class. So let's say I have 80% probability of having an object here, and this object has also 60% of probability of being a cat or a dog in the image in the previous example. There's a caveat here. You may know already that neural networks are not, I mean, they need to be trained. They are trained by gradient descent, so they need to be pushed around. And if I want to predict absolute big numbers, it's very difficult to have them converge correctly and quickly. So you have tricks like rescaling coordinates from 0 to 1 in the landmark detection, or using the hyperbolic tangent to keep the span of the output of layer constraint. But in this case, we really want to use different coordinates in the image. So there are several tricks that are used in the object detection networks that are worth mentioning. First one is let's not predict the absolute position, but let's start from a set of priors on a grid, and we ask the network to predict the offset or the shifts vertical and horizontal position from the grid cells. And then we can do the same for the width and height of the network. And we don't predict them directly, but we provide a pre-computed set of anchor boxes that have a given size and aspect ratio. And what we predict are the scale factor that will multiply the width and the height. So this way, you see we are providing this constant array that contains our priors to the network. And you can even pre-compute the priors on your dataset or on an effective dataset of real images to make them more meaningful. And then this way you can greatly simplify the job that the network has to do. And this will help the convergence a lot. So once we have this all the ingredients in place, we can see what happens with the network results. So in this specific implementation of YOLO, we have a grid which is 13 by 13. And we have also provided 5 size priors for the bounding boxes. So in total, the network will generate 845 prediction. And this is a fixed number. So the network will generate always this amount of prediction and try to make them all good predictions. So in the end, we have 3 results: the boxes, the condition probability, and the objectness factor for a bounding box. Let's have a quick look inside and see what these boxes correspond to. Oh, here it is, trying to render a lot of rectangles. So here are all the rectangles that have been predicted by the network, and I scaled them by their objectness value. So the more probable an object is, the more probable the box contains an object, the high probability of a box containing an object, the thicker the rectangle is. And this is like for all type of objects. But then we have condition probabilities, so we can check, for example, at what is the condition probability of having a cat in the box. And if you remember the original image, we see that the cat was on this side. So like all the boxes here now are the one with the highest probability, and all the other were suppressed. Or we can check for the dog. And again, here we have a different set of boxes that have been highlighted. So let's move down to see how this performs on the real image. Okay, this gives me 2 rectangles, which is exactly what I expect. This final value doesn't look too high, but you have to consider that this is a condition probability, so it's been pre-multiplied. And if we highlight this on the image, we see that indeed we got quite good correspondence between where the cat and the dog are in the image. And here, I rushed this a bit, so I'm close to the end of my talk. I just have one final example that it's live, so you get a look at me, and this will hopefully work. And given that this network is pretty fast, hi, this is me, and given that the talk is almost over, I will soon celebrate with the glass. Is exactly a wine glass, and I will pour a bottle. This to show that you can also build real-time application, and of course now I don't have time to show this in great detail, but you can for example take an application like this and deploy it on the I'm staying here, and deploy it on the web with Cloud Deploy, and you can have all kind of neural network application served to your colleagues or your customers or like all kind of different people. So thanks for paying attention to me, and I guess I'm staying here till the end because this full screen, oh yeah, here it is. So I use this to say goodbye, and we are going to have a Q&A session very soon, so stay tuned. And again, thanks for your attention.
All right, Marcus, if you wanted to share first and mic up and answer some questions, you are free to do so.
Mute. Hello, everyone. So I see we made it without losing too many attendees. That's great. Thanks for sticking with us. We were both busy trying to answer questions, and I think most of the questions got answered. There may be a few big topics. One topic that I'd like to try to answer is what about autoencoders? A topic that I would have loved to include, but time is a limitation factor today, so I didn't put it in the original talk, but maybe I can give an example of an autoencoder right now and here. And another topic, which I'd like to then defer to Julio, because he's the expert on that one, is our integration with the Amazon AWS integration. So if you don't have a GPU at home and cannot do demanding calculations, training tasks, there's still an option that you have in the cloud. All right, let me try to find my autoencoder example. That could take maybe, hopefully not too long. Oh yeah, okay, got one. So this is an example that goes back to the Linette network and the MNIST data set. So what I'm loading here, hopefully this will work out of the box as it is right now. This is an idea of learning about digits or handwritten digits without utilizing the labels. And okay, so what I will do here is I'll just load again the resource for MNIST, the training data, the test data. And then what I'm doing now is I want to do a classifier network, but I have here what's called a simple autoencoder network. The idea is very straightforward. Assuming you have images, but you don't have labels for them, what could you compare the image with? Of course, with itself. And for that matter, in order for the network to learn something, you have something like a encoder network, somewhat similar to on a classifier network that we discussed an hour ago. So essentially convolutional networks, RAMs, and so forth that take image data and then try to compress it. So there's a bottleneck in the middle. So you basically will try to compress the amount of information in an image to a few channels, well, maybe a few hundred channels, maybe a handful of channels, depends what the image is like. And then, since you cannot learn these networks here, the activity of these neurons, you can have a generative network again. So that's a generation part that basically deconvolves. There are also deconvolution layers, well, maybe inverse convolution layers, it should be called, or transposed convolution layers. It's not deconvolution, strictly speaking. Anyway, layers that somewhat do the opposite as convolution. They expand the data again, and the idea is here to regenerate the image so that what came in looks very much like what comes out here. So a network that would satisfy this is this particular one. It's an autoencoder with an encoding a network that has a convolution layer, a ramp, convolution layer, a ramp, and so forth. And then a deconvolution layer in the decoder, pretty much mirror-wise. And last but not least, I have also a loss layer here, cross entropy layer that then compares the input with the output. So the entire network is down here, and it looks like this. It will essentially take input. At the end of the day, it will be noisy input. That's the whole idea of this network. Of handwritten digits, and then it should try to decode it, and the output should be the clean image of the the image that we have. So essentially, we take the handwritten images, we add noise, feed the noisy image into the encoder and decoder, and hopefully we have generated here image, a denoised image of the incoming digit, and that's being compared with the original digits, and that is here done via cross entropy. So that is then okay. This is, I think, an older version that I built this on, so I'm not sure if this is going to work or not. Did I use everything? Okay. Noise encoder. Why? Okay, I won't evaluate it here. This may take time anyway, but I will just call this up. So this is a trained version now of the encoder, and that I can then run on a noisy image and see what it does. So I just extract the encoder part, put in a digit, and reconstruct it, and I get basically the same thing out. So that's already promising. And I can run this now on noisy images and run this through the constructor here and obtain clean version of the noisy input. Now this works exceptionally well because the prior here is that you have numbers, and if you can basically train the network on that prior, then the obstruction of the noise can be quite substantial, and pretty much like a human being, you will be able to pick up still the number that's being hidden by the noise, pretty much like a human being, because you know it's a number, you know what kind of numbers there are, what shapes they have, all that is in the network, and therefore that network can process that noise better than any ordinary noise reduction filter that would not have this prior knowledge about handwritten digits. And here is just another plot of comparing it. So, yep, that concludes a little excursion into autoencoders. I unfortunately don't have an example of more extravagant autoencoders right now working, like a variational autoencoder or even disentangled autoencoder. That's the latest development, but that example I still have to build. All right. Over to you, Julia. Are you ready?
Hello?
Yep.
Do we still have time to go on with the question answer, or I'm not sure how we
Well, what?
Yeah, we can do a few more minutes of Q&A before we wrap up. If you've got some questions you'd like to answer, or just anything else you want to show before we close up, that's fine.
Okay, so generic thing. Okay, things I was showing to people in the question panel. So people ask me about a lot of questions about retraining, and so actually it's very easy to.
Julia, could you increase your notebook to 125, please?
Yep.
Thank you.
Sure. Sorry. And so people ask me about retraining. Let's see. There are basically two ways to train a network in net model, so net train, that are done automatically. So when you have a network like this with uninitialized layers, that means this convolution layer, they don't really have anything in the weights and biases, and also the linear layer, they are completely empty. In this case, net train will automatically call something called net initialize, and this will create. This net model has no input, so. I will show you with a convolution layer. Convolution layer, let's say we have like 5 channels, 3x3 convolution. This, of course, will fail because the convolution layer is completely a symbolic object. So I don't really know how big is the thing coming in. And if I want to put numbers in here, I need to know how big is the input expected to be. So I can do input, for example, this is going to be a 3-channel 100 by 100 image. and them. Now, these layers contain actual numbers. So this is what net training will do on an uninitialized network. But there's no reason to do this if you already have a network. So if I get another net model and I get the standard layer net, which is trained, then these layers, they do contain numbers. And if I call net train on this, I will start from this exact status in the training, so that you don't lose any of the information that was here. And actually, you can use this. You can stop the training at any point, or take any network that you're generating with our checkpointing system and restart the training from there, so you don't lose any information there. One thing you may want to do is you may want to, let's say that you have like pre-trained certain layers, let's say all of them on some task, and I just want to retrain the final classifier, for example, on another task. So I want to fix the weights and biases of the convolution layer. And I can do this via learning rate multipliers. So learning rate multipliers will allow me to say, to settle basically as the multiplier factor for the update step for each layer. And if I set this to 0, the layer won't be touched. So this is an effective way to do fine-tuning on the network. And let's say this was one of the main things that was asked. Let's see, there were another question that I got that was interesting, but now I cannot find it anymore. So I guess there are not any more questions in the box. I will just call it a day, and we can finish here.
All right. Well, thank you so much, Giulio, and thank you, Marcus. That is going to, that'll conclude our presentations for today. We hope you enjoyed learning about image processing with deep neural nets. An email will be sent to everyone in today's audience with a link to the webinar recording and the download links for the presentation notebooks. Remember that you can obtain a free trial of Mathematica from wolfram.com and try all these examples for yourself. We look forward to seeing you online again May 30th for the third and final webinar in this series, when our topic will be deep learning for audio analysis and natural language processing. As always, you'll receive a reminder email about this session. I wanted to remind everyone that we also are running a data science webinar series kind of in tandem with this machine learning, and that continues 1 week from today. I have the link on the screen right now, and that will also be shared in the chat. As you exit today's webinar, a survey will appear, and please fill this out as we use the survey results to guide us in making important decisions in the Wolfram technology stack and adding the features that are most important to our user community. Thank you in advance for your feedback. We will see you next time, and have a great day.